not increased because it's a rare event. Just like in seismic events, we don't increase earthquake loads. It's already, increase is already built in, or the risk associated with spectral exertions are already built in. So this is the load combination we use to design. And then there are two other factors that we multiply specified material strength. One of them is strength increase factor. This is not that important. Strength increase factor is we use safe values for material strengths. For example, in Canada, our design strength is for reinforcing steel 400 MPa, right? But in the lab, constantly we get 420, 460 MPa. In other words, specified strength is higher than design strength. So because blast is such a rare event, so the code committee decided maybe we should give advantage or the benefit of this increases in materials that we know exists, and we don't need to be all that safe because it's such a rare event. So this is why you're allowed to increase concrete strength and steel yield strength by 10%. But more importantly, you have to consider dynamic increase factor. And dynamic increase factor is the strain rate effect. Okay? So if you put your cylinder, or I don't know if you do cube testing here, but your concrete sample into a machine to establish its strength, then you get the solid line, which is under static loading, right? It takes maybe 15, 20 minutes to finish the test. But if you apply this load very rapidly at high strain rates, the strain that you induce is very high, as in the case of blast, material doesn't have a chance to fail. It's just like milliseconds, you hit, material is about to fail, but load is gone. So there is strain rate effect, and under higher strain rates, materials have higher capacities. So this dashed line is what is accepted by the standard for use in design. This is called dynamic increase factor. In fact, here it shows concrete tensile capacity and concrete compressive capacity. We're talking about 30%, 40%, 50% increase. Significant increase if strain rate is very high. Usually, this is the blast strain rate, this is the impact rate, and this is earthquake rate. So during earthquakes, dynamic increase factor is about 1, so we ignore that. But for blast, we may consider that. And these are the test results, and we recommended equations for dynamic increase factor, which is shown for different strength concretes in blue lines. And the European standard CEAB suggested average value irrespective of strength, which is the red line. But the vertical axis is the amount by which you are allowed to increase strength for design purposes. This is for reinforcing steel taken from ASCE based on grade of steel. We usually use grade 60 KSI, which is equivalent to 400 MPa steel. And you can see that steel yield strength also increases quite significantly due to dynamic load effects. So these are the tables now I will show you for flexural, concrete, compression, axial compression, diagonal tension due to shear. As you can see, we are permitted to increase concrete strength 10% to 20% to account for dynamic increase factor or strain rate effect, and steel yield strength again to 20%. Okay, so then we're approaching to the end of this design presentation, and general design approach involves you first come up with design basis threat. This is the charge weight and stand-off distance, and you decide on level of protection, or the building owner decides on level of protection. You do your analysis to see what is the demand in terms of strength and ductility, and then you provide continuity and deformability to make sure that you meet those target levels. And then last step is, after designing individual members, you now do progressive collapse analysis. Now, progressive collapse analysis is done to make sure that failure of a single element doesn't lead to a whole bunch of series of failures. That's what progressive collapse is. And this is typically done applying columns. Now here at the top, you have ordinary building. As you all know, we have negative reinforcement for negative moment at the top, positive reinforcement for positive bending, and even though sometimes we continue down, but theoretically, all we need is here, and you may not have sufficient positive steel in negative moment region. But if you remove this column by loss, then of course you have positive moment for which you did not provide reinforcement, so then the whole thing may come down. So what we do is we provide integrity steel, even if negative moment region develops positive moment, it remains intact, and there are also retrofit techniques for that. So US GSA document provides guidelines. They say remove one exterior column on the short side and see if it works. Remove one exterior column on the long side, remove one corner column, and then do analysis. There are two levels of sophistication in analysis. You can either do static analysis and use maximum dynamic load factor, which is 2. So they say take dead load and 25% of live load, which may be present, okay? Multiply it by 2, because that is the maximum impact of dynamic effect. Usually it is less, but this is simple conservative approach. And then you calculate demand capacity ratio. Demand is how much moment is generated under this load, and then you have unfactored capacity, which is nominal capacity doing sectional analysis. And if it's less than 2, then you're okay. If it's more than 2, you're not okay for symmetric structures. Because this is simple, then they gave very conservative values. For atypical structures, they reduced that to 1.5. But if you have the time, you can afford to do finite element analysis. That's a more sophisticated way of making sure your structure will remain in integral form, having lost a column. Here's an example of how you can do finite element analysis to prevent progressive load. So thank you for your attention. I think it has been a long listening session for you. I hope you're not bored, and if you have any questions, I'd be happy to answer. Yes?
The progressive collapse analysis, it's always static or?
No. You can do dynamic analysis. If you are doing finite element analysis, you can apply those pressure distributions and do dynamic analysis. Static analysis, that demand to capacity ratio, is a simple way of avoiding finite element. You can do that, but that would be more conservative. Any other question?
Well, I think in the interest of time, maybe we should have questions during the coffee break, and later on, towards the end, we'll have questions. So if there is a critical question, you can.
Sure. Great. Thanks again for your attention.
Any question here, Ergen?
Actually, you have worked with one element only all the time. What, for certain cases, there is a combination of elements should be destroyed by pumping. This is not the case. I mean, you have just designed as one beam and convert to single dual feed and work in that. What if we have, for example, 2 columns and beam? What should we do right now?
Okay. So then you do separate and independent analysis for each element. Okay. Let's say you have a column here, but column is a big column, but it is closest to the blast, so the angle of incidence is 0. It has the highest reflective pressure. You do that analysis, but column is so big that nothing happens. Nearby you have smaller columns that are more critical. Next you have to analyze that. But you don't do 2 elements, or you don't do frame analysis. You do one thing at a time. Because of the reasons I explained, it's the frequency of the individual elements that matter.